This video will be doing a two-sample equal variance t-test, also known as the pooled variance independent sample t-test. We're actually going to be doing a two-tailed version of the t-test. And so two-tailed t-tests are ideally suited for a confidence interval, and that's what we are going to be using in this video, though it's not the only way to do it. We could use a p-value. We could do it by comparing it to a critical value, but confidence intervals are actually really nice ways to go. So this test is based upon two independent random samples from two normally or approximately normally distributed populations, and importantly, with the same variance. If the assumption of equal variance is not held, then you'll have to do a different kind of a test, which is called the unequal variance t-test. And the degrees of freedom for that test is a real hassle to calculate by hand. And I would never ask a student to do that by hand. But any statistics package will do that with no problem. But what we're going to do today, we can actually do by hand. It's a little annoying, but it's not the worst thing in the world. So here's a typical example on how we might see this kind of a two-sample t-test. A politician wishing to save money on education by decreasing the number of teachers conducts the following study on reading scores of 8th grade students. She randomly samples students from classes meeting 5 days per week, which we'll call regular teaching, which we will call group 1, and students meeting 2 days in class and 3 days online, which we'll call group 2. She wishes to test whether there is a significant difference in reading score improvement at the end of the semester at the 5% significance level. And perhaps a politician might want to do this because if there's no significant difference, we might be able to use fewer teachers, which some politicians might want to do to get rid of some teachers and replace them by computers. But other politicians might hope to show that there is a significant difference. But anyway, let's just go right into the statistical test. So here's what the data could look like. So here we have the different types of teaching methods. We have regular teaching, which is group 1, and group 2 is 2 days in class, 3 days online. Now, I made up this data, so this is completely hypothetical data, so I don't want anyone watching this video to think this is real data, because it isn't. But in any case, this certainly could exist, and let's say the mean improvement in reading scores for group 1 was 19.98, and for group 2 it was 13.16, and these are the respective. Now, it's important to know that these are sample standard deviations, not population standard deviations, because these are observed from a study. In any case, the assumptions, like I said, are that the children's reading scores are sampled randomly. Both populations are approximately normally distributed. And importantly, the population standard deviations are assumed to be equal. Now, clearly, these sample standard deviations are not exactly equal, but they should not be significantly different. And that would be Levine's test. If you're in a more advanced kind of statistical setting, and maybe you're taking a second or a third course in statistics, and you want to actually test whether the standard deviations are not equal, you're not going to use the F test. You're going to use a better test like Levine's test. But, that's for more advanced viewers of this video. So anyway, I want to show you exactly how to roll through this. So I have a video already out there which talks about how to pool the variance. And hopefully you've watched that video already. But if you haven't watched that video, there's this little formula here. And this is called the pooled variance estimator. Now, this is actually the degrees of freedom from the first sample. This is the degrees of freedom from the second sample. And you might remember the fact that if you take n minus 1 times s squared, you get the sum of squares. So if you remember this, and if you don't know this, you could look at my video on pooling the variance. I go into it in great detail. But the point is that what this is doing is, this is getting the sum of squares from the first group. This is getting the sum of squares from the second group. We're dividing by the total degrees of freedom. And when we plug these numbers in, what we get is 91.973 for our pooled variance estimate. Well, let me write this down. Pooled variance estimate. And that's this. And we're going to use this. We're going to get a 1 minus alpha 100% confidence interval for mu1 minus mu2. And the reason why I'm using the 1 and the 2 is because I called the regular teaching group 1, the first group, and I called the 2 days in class and the 3 days online, I called that group 2. So I'm calling it group 1 and group 2. So here, this is the mean improvement in reading for the first group. This is the mean improvement in reading for the second group, but these are population means. So we are going to be making hypotheses about this. So let me give you the formula. So it's x1 bar minus x2 bar plus or minus, and it's going to be plus or minus, and then it's going to be t sub alpha over 2 times the square root of s sub p squared over n1 plus s sub p squared over n2. And this is the confidence interval formula that we are going to use. Now, I didn't give you an alpha value for this, and in the real world, I'll put that in quotes. Very often college professors hate that term, real world. But in the real world, every college professor who teaches statistics has to admit that alpha equals 5%. And because of that, we use the 95% confidence intervals, right? So these are just the default in the real world. And the reason why that alpha is 5% as a default value for the significance level in the real world is because this guy named Fisher back in the 1930s says 1 out of 20 seems like a good number. And he was one of the founders of statistics. And so the 1 out of 20 is 5%. And he said, it seems like a good number. It's stuck. So in any case, I want to plug these numbers in. I want to get the confidence interval, and I want to see if there's any significant difference between the two groups. So let's plug it in. So we're going to have 19.98 minus 13.16 plus or minus. Now here, this t value, right? Now I should tell you, this t value is going to be t sub 0.025. Now how did I get this? Well, we're going to be using a two-sided test, right? I told you that in the beginning. We're going to be using a two-sided test. And the reason why we can use the two-sided confidence interval is because we're using a two-sided test. That's why we have the plus or minus. So what we have to do here is we have to share the area in the tails, which represent the type 1 error rate. If you remember, the significance level is the type 1 error rate. So if we have a total of 5% and 95% inside, right, that means there's 2.5% on the left tail and 2.5% on the right tail. And if you convert 2.5% to a decimal, we move this decimal point 2 places to the left, and we get t sub 0.025. And I should tell you the degrees of freedom in this is n sub 1 minus 1 plus n sub 2 minus 1. That's the degrees of freedom. So this is the degrees of freedom, and this is the right tail area. Now, I wrote right tail area, but it's also the left tail area. You know, it happens to be, you know, this is a symmetric distribution, but, you know, typically in this notation, this subscript refers to the right tail area, even though I am being completely clear that the right tail area is the left tail area. Now we're going to and this whole thing is called a critical value. This is one symbol that represents a critical value. And I'm just going to call it a crit for the critical value. But this is one single symbol that we're going to look up in the table. And we're going to multiply this by the square root. And we put this over here already. Now, the pooled variance estimate we already got. And we saw that if we did this, if we put this into the calculator, which is a video in itself, which I already did, which is up for you guys, what we get for the pooled variance estimate is 91.973. So I'm going to write this down. And the numerators, so these are the numerators. Now, these are already squared. I want to emphasize the fact that the pooled variance estimator is already squared. If we wanted the pooled standard deviation, we would take the square root of this thing. But this is already squared, so we don't have to square this. It is already squared, and I'm emphasizing this because some students get this wrong. So now the number in the first group is 11. That's the sample size in the first group. And the sample size in the second group is 15. Right? So these are sample sizes, not degrees of freedom. So just make sure you got that right. Now, what is this? So here, let's get the degrees of freedom. So 11 minus 1 is 10. 15 minus 1 is 14. So this is 10 plus 14, which equals 24. So there are 24 degrees of freedom here. Right? N1 minus 1 is 11 minus 1, which is 10. N2 minus 1 is 15 minus 1, which is 14. So there are 24 degrees of freedom. So what we need to do is we need to find t sub 0.025 with 24 degrees of freedom. And let's look this thing up in a little table. So I'm going to go to my student's t distribution, which I have right here. And I have to go to 24 degrees of freedom. So with 24 degrees of freedom, if we look up at the 2.5th percentile, now this would be when you have 2.5% of the area to the left. You see we have negative 2.0639. I hope everybody sees that. See, here's 2.5. Scroll down with your finger. Negative 2.0639. So I'm putting that in my little diagram. Negative 2.0639. And this would make it positive 2.0639. Let me make sure that can be seen right here. So now what we're going to do is we are going to take our 19.98 minus 13.16 plus or minus our critical value, which is 2.0639. And we're going to multiply it by our estimated, it's actually a standard error of this estimator. That's what it is, and we're using this pooled variance estimator. It's a little on the complicated side, but it is what it is, you know. And you have to know this. If you're going to proceed into analysis of variance, you actually have to know this pretty cool. So let's put it in. So we have 91.973 over 11 plus 91.973 over 15. Now, some books factor out the pooled variance estimate, and they put it as a nice little expression all factored out. The reason why I'm not factoring out this, it'll give you the same exact answer, but I'm not factoring it out because I want you to see the structure of this variance estimator. Because if you've worked with this before, this structure will look very familiar. And if it hasn't, if you haven't really worked with this and you're just using the formula, use whichever one you want. You'll get the same answer. It doesn't really matter. So let me show you how to actually do this on the calculator. 19.98 minus 13.16. And then I always subtract first. And we're going to subtract the critical value, which is 2.0639 times the estimated standard error, which is going to be, so now we have to put the radicand in parentheses. So now we have 91.973 divided by 11 plus 91.973 divided by 15. And then we're going to close the parentheses to tell this calculator that the radicand is this one term. And then we're going to hit the equals button. And we are going to get negative 1.0, negative 1.0, let's say 37. It's a little more precision than we need, but I'm going to put it in anyway, right? So I hope that's clear. Now this is called the lower bound of the confidence interval, just sometimes called an LB. So now what I'm going to do with my nice little calculator is I'm going to scroll back. I'm always talking up this calculator. I should try to get an endorsement from Casio because I use this calculator all the time, but they don't even know who I am. So now we're going to change this minus to a plus. And on this calculator, it's really easy to do. I just overwrite the plus. Make sure you change the correct minus. Don't change this minus into a plus, right? You change this minus into a plus. If you change this minus into a plus, everything's all screwed up, you know, so don't do that, right? So now I'll just bring my little scroll wheel back, and then once I hit equals, I will have my upper bound, which is 14 point, oh, it's hard to read with the glare, 14.677. All right. So now the next, and well, the final step, and this is called the upper bound, sometimes just the UB. So this is a 95% confidence interval. So what we're saying here is that somewhere, right, there's a true mean difference, right? And let's just call it mu1 minus mu2. This is the population mean difference or the true mean difference. And if we were going to replicate this experiment over and over again, you know, each time we'd get a different confidence interval, and it would, you know, some would be narrow, some would be wide, you know, they'd be moving around. But approximately 95% of the time, this confidence interval would cover or capture this true mean difference. Now, the human being doesn't know what this true mean difference is, because if we knew, we wouldn't spend the money and the time to do a study. That would be ridiculous. So we form this confidence interval, and it's a 95% confidence interval. So 95% of the time, this confidence interval is capturing this true population mean difference. So this confidence interval can be as low as negative 1.037, and it can be high as 14.677. But how do we interpret that? Well, let's write the hypotheses. The null hypothesis is that there's no difference in the population means. Now, how's another way to write this? Mu1 minus mu2 equals 0. This is what no difference means, zero difference. We are looking at a two-sided alternative. So our alternative, we're just looking at that there is a difference. Right? In other words, mu1 minus mu2 is not equal to 0. Because if there's a difference, then this difference is a non-zero difference, right? So what we have calculated is we have a confidence interval, a 95% confidence interval, of negative 1.037 all the way up to 14.677. And the thing is, this confidence interval captures, some people say covers, the hypothesized mean difference of 0. Right? I want you to notice that, because that's really the whole thing. We're hypothesizing that there's no difference. That's the null hypothesis. And you'll see if we make a little number line for this confidence interval, right? And we go from negative 1.037 all the way up to 14.677, you'll see that the hypothesized value of 0 is somewhere around here, drawn to scale as best as I can. So since this confidence interval captures or covers the hypothesized mean of 0, we have to conclude that there's no significant difference. So this confidence interval captures or covers the hypothesized mean difference of 0, from which we conclude no significant mean difference at the 5% significance level. Now, how do we put that into practice? Depends on it depends on the politician's motives. Because the politician can say, well, look, hey, there's no significant difference between the reading improvement based on whether they get the regular teaching or whether they get 2 days in class and 3 days online. There's no significant difference in improvement. So, hey, we have a budget to deal with, so let's just fire a few teachers and, let the computer handle the remaining teachers. Now, I'm not saying that's good. I'm not saying that's bad. Obviously, I'm a professor, so I'm not really too happy about firing teachers for many reasons. But this is, this is something that could certainly come up. There's no significant difference between the more expensive, which could be the standard status quo method, the regular teaching, and this new, technology supplemented, method of instruction. Fortunately, this is hypothetical data. I just made it up. This isn't a real study. I only made it up to illustrate this method. But I want everyone to see that, this is stats could easily be applied to in the real world. Now, I want to emphasize this idea that if this confidence interval did not cover the hypothesized mean difference, then we would reject the null hypothesis. And there's actually 0 is the most commonly hypothesized mean difference, but we didn't have to hypothesize a mean difference of 0. We could have hypothesized a different mean difference, and then our interpretation would be different. And indeed, that's one of the strengths of the confidence interval approach to hypothesis testing. But I don't want to go through that in any great detail here because it's a more advanced idea. And so I am going to end this video with the fact that since the confidence interval captures or covers the hypothesized mean difference of 0, we must conclude that there is no significant mean difference at the 5% significance level, telling us at that level of significance, it doesn't matter whether we use regular teaching 5 days a week with a real human teacher, or whether it's 2 days in class with a real human teacher and 3 days online.